So first, some of the stuff like we did in class, identifying the conjugate acid-base pairs. So remember, conjugate pairs differ only by H+. So which thing on each side of the equation is, which two things are basically the same except for H+. And so that would be these two and these two. In this case, this is the acid, and this is the base, and this is the acid, and this is the base. You see that? Okay. Next one, it's these two and these two. They won't always be written exactly in the right order like that, but they usually are. And so I wasn't like trying to give you a hint necessarily. That's just usually how we would write it to be the most clear. So in this case, this is the acid, base, acid, base. Okay, acidic, basic, or neutral. Laundry detergent at a pH of 9.4. What do you think? Basic, yeah. Honey, acidic. And this was the tricky one because you had to do some calculations here. If the OH, the hydroxide ion concentration is 1 times 10 to the minus 5, that means the POH is 5. And then what does the pH have to be? So what is that? That's basic. Okay. And what was your way of remembering that again? I was just trying to remember it from my other class, but I couldn't remember.
It was, you think you're 10? Yeah, on the pH scale because you're basic.
Okay.
I don't know. It's
That's clear.
stupid. It just helps.
No, it's good. It's good if it helps you, if it helps remember it. I think it would help other people too. All right, I'll try to remember that. Mm-hmm. But not to actually say to people, but like as a way of remembering. It has a base, yeah. It's a very specific insult also though, because you have like the person you're insulting has to understand what that term means as an insult. Yeah. Yeah. All right. Anyway, rate balanced equation for the complete neutralization of sulfuric acid and by, that should just be by sodium hydroxide. So that would be sulfuric acid. There's a list. If you didn't see it, make sure you go look at it on Blackboard of acid formulas and base formulas that you need to know in the objectives for the chapter. So that's sulfuric acid. Sodium hydroxide is NaOH. You should know that from lab and from naming compounds and all that kind of stuff. And since it's complete neutralization, we don't need a double-sided arrow, but if you put one, that's okay. Complete neutralization assumes that it's actually going in that direction. So the complete neutralization forms what? Neutralization always forms something. Do you remember from lab or anything? Neutralization always forms water. So water is always a product of neutralization. You take an acid, a base, combine them, make water. And then the other product is what's left from the other stuff, which is the sodium and the sulfate. Now that's complete neutralization because both of those hydrogens on the sulfuric acid can come off. But if you did it this way, that's okay too. That's like an incomplete neutralization, but that's okay. That's not balanced though, that's not okay. So we have to balance it by putting a 2 here and a 2 here. If we did it the bottom way, it would be balanced without any extra coefficients, and that would be okay. So neutralization reaction, acid plus a base makes water. And then the other tricky thing about this is remember that when we add sodium hydroxide, really the base part of that is just the hydroxide, and the sodium is just kind of hanging around for fun. So when we think about what's really happening, the hydroxide is taking a hydrogen from the acid to make water. And that's what it's doing. All right, that was the quiz. Quiz 6, that's not right, it's quiz 8, right? Yeah, quiz 8, I didn't change that in the PDF part. So we will have another quiz next week. Wait, is next week Thanksgiving? No, we got another week and then Thanksgiving. Yeah, so we'll do a quiz on nuclear stuff next Thursday, a week from today. And that'll be the last quiz before the exam.
How many are we going to drop?
No, probably not. We'll probably have one more quiz. But
how many are we going to drop?
We will keep 5 quizzes. So we'll probably have 10 or so, 10 or 11. And so we'll drop 5 or 6 quizzes. Yeah, so today we're going to finish up talking about nuclear chemistry, practice some problems with that. And then next week starts the organic chapter, which is chapter 11, I believe. Yeah. That's a really long chapter. So we won't finish that chapter 11 before the first exam probably, which means that whatever we get through next week, that will be the cutoff for the exam, because the exam's then after Thanksgiving. We will get through, or whatever we get through that Tuesday before Thanksgiving, then that will be the that will be what's on the exam. Yes.
And then the day of the exam, we also have a paper too?
No, we didn't end up doing that this semester.
Oh, okay.
Yeah. I think we talked about that at one point. There was, yeah, in the syllabus, there's a thing about like a research paper due, and we kind of just decide throughout the semester if people have time and want to do that, but we decided against it this semester. So, yeah. Okay, am I right on the schedule there? I think so. Next week's, then, yeah. All right, so last time we talked about some of these different reactions that were very, very different from all the stuff we've done before, stuff coming out of the nucleus or going into the nucleus, that kind of a thing. We're going to continue that today. So we looked at how we can kind of balance the numbers on each side to figure out what's going on in these reactions, what's coming out, what kind of particles, that kind of thing. Today we're going to look at the other 2 pieces of that, which is the measurement side. Like how much radiation, how much stuff is coming out of these compounds. We're going to look about measuring radioactivity. So if you have a radioactive thing, this is my best picture of a rock, radioactive rock. There are 2 ways to measure radioactivity. There is the radiation coming off of the rock. So let's say those are beta particles, right? So you can measure how much is coming off the rock. And I guess let's do that first. How much radiation is being emitted from a source. And the way that that is measured is, we can think of it as like particles per a certain time unit. There's a picture in the book about this. Grab that. So you'll see a couple in there if you're reading through in section 5.3. The main ones are the Curie and the Becquerel, and they both measure disintegrations per second. In other words, how many nuclei are disintegrating or decaying per second, because each one that does is emitting a particle. So that's directly, it has a direct relationship with the amount of particles that are coming out. So the two units that we work with for those are the Curie, CI, and the Becquerel, BQ, named after the people who discovered some of the early radiation, Marie Curie and Henri Becquerel. And again, looking at disintegrations per second. So they both measure that. The Becquerel is 1 disintegration per second. The Curie is much larger because it's how much, I think it's how much a certain amount of radium decays in a certain amount of time. So that's the only difference in those two units, is one's smaller than the other. You don't need to know the specific numbers or anything, but we can convert back and forth between them using our normal unit conversion skills if we need to. And I always forget what that number is. There it is. So 1 Curie is 3.7 times 10 to the 10th becquerels. That's, is it a gram of radium in a minute? In a second, yeah. So that's how many disintegrations occur in 1 second for 1 gram of radium. How many individual nuclei are disintegrating and then emitting particles. Okay. The other side then of measuring radiation is how much is being absorbed by something. Because you don't want to absorb radiation, so he's mad, is what I was trying to express with that. So how much radiation is absorbed is a different kind of calculation, because we want to know not just like the bulk amount that has transferred from the source to wherever it's going into, but we need to have it like per a certain unit mass. So the basic idea is, if we look back on this thing, one main unit for this is the rad, which stands for radiation absorbed dose. And this is the radiation per gram. So like per gram of flesh or per gram of material, or whatever you're trying to measure.
Per gram of what's absorbing it?
Yeah.
Okay.
So per gram of the material that's actually absorbing the stuff, like how much is being absorbed. There's a little bit of a problem with that measurement, though. I mean, it's a fine measurement, whatever, but it assumes that everything is the same, that all stuff that absorbs radiation is the same, and that all radiation is the same. And that's not true. As we've talked about, like some of the things are more penetrating than others, some of them are more damaging than others. So what we really want is a human-based, or at least a living thing-based measurement that tells us something about what is our risk. Because when we're measuring absorption or exposure to radiation, we want to know like how much have we gotten based on how much is okay for us, based on how much is bad for us, that kind of a thing. So the one that we use more is the rem. And the rem is actually the same unit as the rad, but with a correction factor for humans. So rem stands for radiation equivalent in humans. So not just like how much is being absorbed by generic unnamed stuff, but what risk is it to humans? And the corrections in this factor are for things like the fact that alpha particles are big, and that makes them much more damaging than the smaller particles. So when an alpha particle hits you, whatever it's hitting is really absorbing more radiation, if we're really talking about the energy that it's absorbing, than if something else hits it. So I think there's a you don't have to know any of these numbers, but there's a table. Or not a table, but they tell you in the text here. The where is it? Oh, here. So for just regular pure energy radiation, which also includes pure energy and beta particles, the factor is 1. If you're getting hit with a proton or neutron, the factor is about 10, and for alpha particles, it's 20. So it's just a way of scaling that to have a better sense of like what kind of damage is this stuff actually doing. Okay. So those are the ways of measuring radioactivity. There's other ones. There's like there's the gray, there's the sievert, which is 100 rem, and then of course milli and micro and all that kind of stuff come in too. You don't have to know those numbers. I mean, you have to know how to convert units, but I'll always give you the numbers like this many of this is this many of this. So you don't have to know those. I did want to look up, take a look at this one site, if I can find it. This cartoonist did a really nice comparison of radiation doses and what they look like. I think this is, well, you can find it, or I can post it on Blackboard if you're interested. But what's going on here, we'll zoom in to see this because I know you can't read all that little stuff, is basically looking from here to here, it's going up. So like this many of the yellows is this many, is all of that put together. This many oranges is all of that put together. This many greens is all of that blue put together. So it gives you a sense of like how much radiation it is for other things. So let's zoom in and take a look at some of these different things. So on the very low end, you've got sleeping next to someone. Did you know the radiation from sleeping next to somebody? And not just sleeping next to superheroes, just like anybody. And that's just because of naturally occurring radioactive elements in our body. Remember, we think of like radiation and nuclear stuff as this really like artificial, done in fancy labs, making weapons and stuff. But most radiation comes from natural sources. Most radioactive things are natural. They come from the earth. So anything that has stuff from the earth, anything that's made out of atoms, is going to have some radioactive elements in there that release some kind of radiation. Okay. You want to get twice as much radiation of that, you got to eat a banana. Right? Also get some radiation from that. Then we're talking about power plants, which you don't get from the generation of the power, but more just the coal itself is going to have radioactive particles in there. Arm X-rays, using a monitor, this kind of stuff, dental X-ray. And then you put all that together, and this set of blue boxes, about 10 microsieverts, is how much we all get, how much radiation we get every day, ionizing radiation. You take an airplane flight, you get more. Why do you think that is? Airplanes made out of radioactive material? No. That's not what we're measuring though, because this is just talking about like ionizing radiation or nuclear radiation. It's just because you're up higher is what it ends up being. It doesn't have anything to do with the airplane itself, but if you're up in the atmosphere, you have a lot less atmosphere filtering out that radiation that's coming from space and wherever. And so you end up being exposed to a little bit more of that. All right, let's jump over a little bit here to get a sense of size. So all of that blue stuff put together is this little bit, 3 little green boxes. Okay. And the maximum yearly dose permitted for you, if you're a radiation worker, that's your job, this is the most radiation you can get in a year, And basically they're saying you're probably still gonna be fine if you get that much radiation. So if you're in the public and you're not, this is how much radiation you should be getting. And if you look at that, you get half of that just from the natural potassium that exists in your body. So we're exposed to this stuff all the time. A nuclear power plant, yearly release limit is way less than what you get from your natural potassium in your body. And that's like the limit. The target for what a power plant should release is almost nothing, is even smaller than like some of these silly ones that like bananas and whatever. So very, very, very small amount. So the idea that you get exposed to radiation from like being by a nuclear power plant or something, it's not true. There's just not that much radiation coming off of those things. If you get a chest CT scan at the hospital, it's a type of an X-ray, that uses a lot of radiation. And now you're kind of starting to get in that range where like maybe you got to be careful. So most healthcare places will keep track of how many chest CT scans you get in a year. And they'll say, well, you've probably been exposed to too much radiation. We probably shouldn't do this again unless you really need it or something. They'll keep track of that because that does start to increase your risk. All right, so now all of that stuff put together is like 7.5 orange squares, and now we start getting into those dangerous, the dangerous realm. So if we got all of that a few times, we could start getting some radiation poisoning, where the radiation is damaging us, damaging our body. And severe enough to be potentially fatal would be a lot more than that. But remember, these are orange boxes now. So this is all that stuff combined many, many times. All that other stuff combined many, many times. And then once you get up here, you are talking about fatal dose. So radiation can kill you if you get a large amount of it at once. And then if you were right next to the core during the Chernobyl meltdown, which people were, that's how much radiation you'd be getting. So all of that fatal doses multiple times over. So that's the biggest. All right, so what information do we take from this? I think there's two things we take from this. One, that we have to be careful about radiation, that it's dangerous, that it can make us sick, that it can hurt us. But also, you need a certain level of radiation to reach that point that we are almost, well, pretty much never exposed to. So the idea that we need to fear or be afraid of or avoid these very low doses of radiation is false, right? Because we know that the normal kind of radiation is far, far less than what we would even just get from natural processes. And maybe that doesn't seem like such a big deal, but like one of the things that's come out of this, has anybody heard of irradiated meat? Nobody? Nobody's heard of that? Okay. That's kind of sad, but let's talk about why that is. It's in here somewhere. I'm not gonna look for it, but it's in the book. So there is a process by which you can pass gamma rays through meat and kill all the bacteria that's in the meat from the gamma rays. So you're talking about high exposure of gamma rays to the meat, which kills the meat, or which kills the bacteria in the meat. So it's a way of pasteurizing meat and getting rid of foodborne illness. There's not a health risk from the irradiation itself, because after the meat is irradiated, then the radiation is like the gamma rays aren't there anymore because it went through there, and so there's no more left in the meat. There is a tiny, tiny bit of damage done that leads to some, like, whoops, blue levels of radiation from that meat, which a lot of that was there anyway. But there is some creation of radioactive isotopes inside that meat as a result of that gamma radiation. But as you said, you haven't heard of this stuff. You can't really buy it. It's not popular. And it's because people are scared of it, that it's that we use nuclear stuff in our meat and it's radioactive. And that's actually really sad, because that had the possibility of saving lives. Thousands of people die from foodborne illness. Like, that's an actual thing that's killing people. Tiny doses of radiation don't hurt anybody. But since the tiny doses of radiation are more scary to us, then we basically have said, don't sell us this meat. This meat is garbage. We don't want to eat it. And I think that's kind of a sad result of just people not understanding the science of the nuclear chemistry involved. That you're not eating like a nuclear bomb or something. I mean, some people think that when you microwave food, you make it radioactive, right? We have that phrase, like to nuke your food if you put it in the microwave. And a lot of people legitimately think like you're making your food radioactive when you put it in the microwave. And that's not true either. But even if it were true, you would be talking about these tiny, tiny doses that we live with every day anyway. So think about that when somebody says, oh, don't eat this, this is bad for you. It's like, well, is it really? Or are we just scared of it because it seems scary? Okay, I broke it. All right, we're back. Okay, so that's radiation doses. And when we do the radiation lab on Tuesday, we will look at some of this stuff and measure it. And I'll show you some measurement devices. All right, so the next thing is measuring decay. And we're going to use a concept called half-life for that. Half-life is not unique to nuclear chemistry. Anybody know what a half-life is?
It's like the amount of time it takes for half of the population that you're looking at to decay, so like the bacteria. It's a common one to use.
Sure. So the time it takes for half of something to not be there anymore, to decay, to disintegrate. And the symbol that's sometimes used for that is T1/2, so the time for half. And the reason I just say something is because it applies to a lot of things. Like you said, bacteria. We can also look at medicine. If you take medicine, you might want to know the half-life of that medicine. How long does it take until there's half of it in your system? And then how long until there's another half of your system? And how long until there's another half in your system? Or whatever, cut it in half again in your system. And that gives you a sense of how quickly you're metabolizing or slowly you're metabolizing that stuff. The reason we use this concept half-life instead of just saying, why don't we just say like when is 10% and when is 20% and when is 30% gone, is because you have a binary situation. It's either there or it's not. It's either still the way it is or it's decayed. So that means that each time it's not a linear decrease. So it's not like you start with 100 of something and then you've got 90 after 10 seconds and 80 after 20 seconds and 70 after 30 seconds and so on. It's not a linear relationship because of this on-off thing. So it ends up being what's called an exponential relationship, which just means that we have to think about it in terms of cutting it in half instead of like decreasing by a certain amount each time. So for nuclear isotopes, it works the same way. Either the isotope has decayed or it hasn't. There's no like partial decay per each nucleus. So let's look at this through an example. Let's say we have 10 grams of iridium-192. The half-life is 74 days. So that information tells us that we can start with that 10 grams, and after 74 days, we now have 5 grams. Now, it doesn't mean that 5 grams like simply vanished. It just means 5 grams turned into something else. They were iridium-192, but that decayed and now they're whatever. Excuse me, depending on the decay mechanism. After another 74 days, we have 2.5 grams. So the first 74 days we lost 5 grams. The second 74 days we only lost 2.5 grams. And that's what I mean by it being nonlinear. So in the same amount of time, you decrease the amount you lose each time because you're always cutting it in half. So after another 74 days, we've got 1.25 grams, and so on. Now, because we're talking about an actual real sample, we will eventually get to 0. It's not a perfectly, asymptotic type situation, but we will get to 0 very slowly. It'll be a little bit around for a long time. All right. We can talk about these overall time frames in a couple ways. So we could say, like, what is this called? Well, one thing that it would be called is however many days that is. So do I have this number? 216 days. 74 plus 74 plus 74. So in 216 days, we've gone from 10 grams to 1.25 grams of this radioactive substance. We could also call that 3 half-lives. So in 3 half-lives, we've gone from 10 grams to 1.25 grams. And this is what I notice confuses people sometimes when we do these kinds of problems on quizzes and things. You've written down 4 numbers. So when you just look at it, you might think like, oh, that's 4 half-lives. I've got 4 numbers. But it's not. It's 3, because this is at time 0. So after 1 half-life, you've got 5. After 2 half-lives, you've got 2.5. And after 3 half-lives, you've got 1.25. So count those arrows. Those 3 half-lives are 1, 2, 3, not the like individual numbers. Does that kind of make sense? Now, there is an equation for this. You can make an exponential equation, like a 2 to the n type thing. We're not going to do that in this class. If you're curious about it, you can look it up and use that to figure it out. Because you can answer the question like, how much would there be after 71 days or 50 days? That is an answerable question when we plot this thing out. We're just not going to do this in this class. So we're going to stick to even half-lives. How much would there be after 1, after 2, after 3, after 4 half-lives, so on. We can also talk about this in terms of the radiation, and that's why we look at those units. So we might want to know a sample of that same stuff emits 80,000 becquerels of radiation. So if you're thinking of this in terms of like medical uses, radiotherapy, that kind of thing, you want to know how much radiation is coming off of that so that you can then give it to somebody and, whatever, that's like the dose. So if it emits that at the beginning, you can't just say, okay, well, take that and then you'll get all that radiation, because eventually it's going to break down. After this time, a certain amount of time, that's going to start breaking down. So we can ask the same questions like, how much that's kind of a clunky phrasing. It should be like, what is the radioactivity after 148 days, let's say. So we've got 80,000 becquerels of radiation. How much after 148 days? We can use the half-life to figure that out too. We need to know how many half-lives there are in 148 days, so we know how many times we have to cut it in half. So how many half-lives are in 148 days? 2. Remember, see that? If 1 half-life is 74, 2 half-lives is 148, because 74 plus 74 is 148. So you got to figure out how many half-lives are in that time frame that you're talking about. In this case, that is 2 half-lives. So once we know how many half-lives it is, we just need to cut it in half that many times. And I always recommend writing this kind of chart down just to keep everything straight, because it's easy to accidentally cut in half an extra time or not cut in half enough times, something like that. However you want to do it that makes sense, that works for you, is fine. So we've got 80,000, not 8,000, to start with. After 74 days, which is 1 half-life, we've got 40,000. After another 74 days, which is 2 half-lives, we've got 20,000. So between here and here, we've gone 148 days and 2 half-lives. And 48 days and 2 half-lives there. Okay, see how that works? Think you can figure this out? All right, let's try some. All right, we need a couple of page here. Sorry. Let's try this. All right, so a radioactive sample with an activity of 12 millicuries is used to study the rate of blood flow in the circulatory system. If sodium-24 has a half-life of 15 hours, what's the activity after each interval? So that last one's going to be a little bit tricky. Make your best guess, but we should be able to do the other ones. How much is left after 1 half-life, after 30 hours, and after 3 half-lives? Give that a try. We'll go through it. One strategy that you can use here is just set up that chart to start with. So you can find out from the equation or from the question how much you're starting with and how much is the half-life in this type of a question. So we know we're starting with 12 millicuries, and we know each half-life is 15 hours. So we can kind of just set something up like this. And then figure out what the question is asking about. Whoops, except that's wrong. So after 1 half-life, means you cut it in half once, you got 6. 30 hours, we can look at our chart and say, oh, 30 is 15 plus 15. So that's 2 half-lives. So that is 3, right? 3 millicuries? All right, let's write these down. So after 1 half-life, you've got 6. 2, you've got 3. 3, you've got 1.5. And then 2.5 days. How many? That's not going to help us. So how many hours is that? That's 60 hours. And so that's 4 half-lives. 15 plus 15 plus 15 plus 15 is 60. 2.5 days is 24 times 2.5, which is 60. So that's 60 hours, 4 half-lives. And so you've got, it's not really equals. So we count 1, 2, 3, 1, 2, 3, 4, the 0.75. All right, let's tell you that kind of question. The other type of question like this is you can figure out the half-life based on some data. But there aren't any questions like that there. So let's see if we can find one. Otherwise, we'll just make one up. Yeah, here's one. If the amount of radioactive phosphorus 32 in a sample decreases from 1.2 milligrams to 0.3 milligrams in 28.6 days, what is the half-life of phosphorus 32? I've asked this problem on a quiz or exam before, and people try to do all kinds of crazy stuff. They'll divide 1.2 by 0.3, or they'll divide it by 26.8 days, or they'll take the difference of the two and divide by 26. You can't do any of that kind of stuff with these types of problems because it's all about cutting it in half over and over again. So I know that one is not a great strategy, but I know that one strategy people use whenever they see numbers in problems like this on exams is just to start multiplying and dividing things until you get something that seems like it kind of works. That's not a great strategy, but it especially doesn't work for these ever because the numbers that you're given, you can't just nicely divide and get, it's not like a unit conversion. So what you should do here is set up that same kind of chart. What are we going to start with?
1.2.
1.2, and then start cutting it in half until you get to 0.3. Let's try that. So we start with 1.2. After 1 half-life, it's 0.6. After 2 half-lives, it's 0.3. Oh, and there we go. So 1.2 to 0.3 gives us 2 half-lives. And that is 28.6 days, which it tells us in the question. So it decays that much in 28.6 days. And if that's 2 half-lives, what is 1 half-life?
14.3.
Yeah, everybody see that? 28.6 divided by 2. So half of that must be 14.3. All right. Let's look at another one. This one over here. So we're going to pull this graph out. So that's what a half-life graph looks like. When you cut something in half each time, instead of getting a line going downward, you get this curve because you're actually losing less each time. Each time you cut it in half, you lose less than the first time you cut it in half. Because how much is left depends on how much there was when you started. All right, so let's see if we can answer these questions about this particular curve for iodine 131. All right. Complete the values for the mass on the vertical axis. So those blank lines that you see here and here and here, and those correspond to, if it's hard to see from where you are, we can connect them here. That corresponds to that one, this one, and that one. So if there's no numbers on the side except for 80 and 20, how do we know what those other masses should be?
Oops. 20 is the second half-life, so you know it goes down to 40 and then like 80,
Yeah.
40, 20, 10.
So once we're told that this is a decay curve, and we know that we're dealing with something like half-life of a radioactive iodine, we know that each point is going to deal with a half-life. So that means cutting it in half. So if you start at 80, and then you get somewhere, and then you get to 20, in between that must be 40. Because you cut 80 in half, you get 40. You cut 40 in half, you get 20. And so then what should we put for those other two? Yeah, 10 and 5, because we're cutting it in half again and then cutting it in half again. All right, what about the days? Yeah, we can look at a pattern there, right? It seems like we're getting a point, so it's cutting in half every 8 days. So we can continue this and say 24 and then 32. So then what's the half-life?
8 days.
8 days. You see that? Every 8 days it cuts in half. So we can use a curve like this to find all that information, how much is left, whatever. We could also use a curve like this to kind of figure out those in-between ones. So if we had a question like, how long until there is only 30 grams left? We could at least estimate it based on the graph, and this is something you'll do in lab next week, where we could look at, say, okay, 30 is probably about here, in between 20 and 40. And so we could estimate that we'd get to 30 at about 10 days or so. See that? Just over 8. Where we get to that. So that's another way we can use that information. All right, let's practice some reactions, and then we can call it a day. So see if you can write a balanced nuclear equation for each of those. And all they're giving you is the isotope and what kind of a decay it undergoes. And with just that information, you should be able to write a complete balanced nuclear equation. You may need to flip back to your notes from Tuesday because we haven't studied that much yet, but take a look at that, see if you can figure that out. All right, so remember how to do this stuff? Think so? All right, so first thing you do, these are all decays, so that means nothing else is on the left side of the equation. If you saw something like neutron capture or proton combines with a proton or something like that, that would be different. Then you'd put that on the left side too. But we're just having decay, so we put that with the arrow, and then we draw our decayed particle. In the case of beta decay, that's going to be an electron. In the case of alpha decay, that's going to be a helium nucleus. And in the case of gamma emission, that's going to be a gamma ray. And then we use the numbers and write what's left. So 19 is -1 plus 20. And 2040, that's going to be calcium. 1735, that's chlorine. 78 minus 2 is 76. 190, that's osmium. 86. Whoops, not 190 though, sorry. Whoops, oh no. We're going to just have to put here, 186. This one minus 4, that's going to be 106. And that is radon. And then the gamma ray doesn't change the numbers at all. We just take off the M. And we still have indium. Indium 113. So is that what you got? All right, great. So quiz on Tuesday or Thursday. You want to do Tuesday or Thursday? I don't actually care. Maybe have strong opinions, one way or the other. We'll just stick with Thursday. It seems to be a good quiz day, I guess. So it'll be very predictable. You'll see equations like this, equations like the ones we did last time, where you have to kind of fill in the missing stuff by adding up the numbers. You'll see half-life stuff, and I guess that's it. Yeah. So all right. Have a good weekend. I'll see you Tuesday.